This video is about monotonicity of functions. When is a function increasing or decreasing, and what this has to do with derivatives. This will be our third application of the mean value theorem. Before beginning, an important clarification. Saying that a function is increasing is not the same thing as saying it has positive derivative. These two concepts are related, but they're not the same. Positive derivative is not the definition of increasing function. Here is why. This is an example of a function that is increasing everywhere, but it has derivative 0 at a point. Or this graph represents another function that is also increasing everywhere, but it has a corner at a point, so it's not differentiable at one point, doesn't have a derivative. Or this is a function that is increasing everywhere, and yet at infinitely many points is not even continuous, let alone differentiable. So a function can be increasing without having positive derivative. We should then define increasing function formally. Here is the definition. I begin with a function defined on an interval I. I want to say what it means to be increasing on I. It's always a function is increasing on a domain. And that means this condition, that for every 2 points, x1 and x2 in I, if x1 is less than x2, then f of x1 is less than f of x2. So that means if I took a bigger input, then it produces a bigger output. And that's going to mean that the graph is always going up. I'm using this definition where I say f of x1 is less than f of x2. There is a related concept, which I'm going to call non-decreasing, in which case I say that x1 less than x2 implies that f of x1 is less than or equal to f of x2. So for increasing, it just means the graph always goes up. And for non-decreasing, it means the graph always goes up or stays constant. Of course, there is also the notion of decreasing and the notion of non-increasing, which will be similar. I assume you can write the definitions, just reverse the second inequality. Unfortunately, this notation is not universal. While some books use this convention and call these two things increasing and non-decreasing, other books use strictly increasing and increasing instead, which is unfortunate because it means increasing could mean either one of the two, depending which math book or which math paper you're reading. There is no way around it, both are used. So if you're reading a paper or a book, make sure you know which definition it's using, and if you're doing math with somebody else, agree on a definition before starting. So that's the definition. And the three functions I looked at before, the three graphs of those functions, satisfy this property. They are increasing. This is an increasing function, this is an increasing function, and this also satisfies the definition, so it's an increasing function. Okay, now we know what increasing means. What's the relation between increasing and positive derivative? So here's the theorem. Let's say I begin with a function f defined on an open interval a, b. Then if I know that the derivative of the function is positive, then I can conclude that the function is increasing on that interval. That's the theorem. So positive derivative implies increasing function, but a function could be increasing without having positive derivative. So that's the theorem for an open interval. There is a companion to this one. If instead I'm looking at a function defined on a closed and bounded interval a, b, if I want to conclude that the function is increasing on it, then I only need to require that the derivative is positive on the open interval, on the interior. But on the endpoints, I need to require continuity. So positive derivative on the interior, continuity everywhere, implies that the function is increasing on the whole interval. These two theorems need a proof, and I invite you to write the proof for it. A couple videos ago, I wrote a proof for a similar result, that if the derivative of a function is 0, then the function must be constant. That was a direct application of the mean value theorem, and this works exactly the same way. So I invite you to rewatch that video. I will add a link in the description, and then try to imitate that proof. You only have to modify it slightly to prove these two theorems. That is a good exercise to make sure you understand the mean value theorem and how to write these kinds of proofs. So, after seeing the theorems and the proofs, here's a summary of what we know so far. On an open interval, if the derivative is 0, then the function must be constant. If the derivative is positive, then the function must be increasing, and if the derivative is negative, then the function must be decreasing. I haven't written the theorem for this last case, but it works exactly the same way as the other. But if I just have a point where the derivative is 0 does not exist, then in principle it could be anything. It could be part of a bigger interval where the function is increasing, or we may have a local extremum at that point, or something else. In the next video, I will show with an example how to use these theorems to determine the intervals where a certain function is increasing or decreasing.